Dr. Jeremy Lundholm, who's a professor in biology and environmental science. His research interests include green roof ecology, species diversity patterns, regeneration and restoration ecology, urban plant communities, and coastal barren ecology. He's been published in a wide range of scholarly journals as well, including Annals of Botany, Environmental Science and Technology. You can understand I couldn't memorize all of these. Ecological Engineering, the Journal of Applied Ecology, Ecological Applications, and the Journal of Vegetation Science. He's also co-author of the book, The Urban Cliff Revolution.
Hi, my name is Jeremy Lundholm. I'm in environmental science and biology. So I'll talk about green infrastructure a little bit, and I'll try to answer the question, how green is my green roof? Of course, I won't actually answer that. I'll just talk around it, but this is sort of framing what I'm going to talk about. So before I came here, I'm an ecologist. I studied little tiny plants that grow in very harsh environments and how they get along with each other and how they survive in these places. When I moved to Nova Scotia, I started studying coastal barrens because they're very similar. It's little tiny plants growing in difficult environments and how they coexist together. By the way, we're now rebranding this ecosystem. We're now calling them Acadian heathlands because we think that sounds a lot better. So, barrens, they're anything but barren. They just don't have a lot of trees. So we're trying to work on that. I also started working on urban ecology and looking at urban environments. You see a lot of similarities with these rock barren environments. They're bad places for plants to live. This was Tower Road a few years ago. This might have been the 5th time they repaved the road that same year. And this is where the vegetation is supposed to go, right? So traditional urban design doesn't provide a lot of good quality habitat for plants. And so, talking about the urban environment, this is familiar to me. It's just an artificial version of what I've already been studying. So looking at urban ecosystems, they're dominated by people. We're the alpha species. What we do controls the flow of energy and material through these ecosystems. From a more ecological perspective, what urbanization does, it replaces plants and soil, so vegetation and soil, by hard impermeable surfaces. And what this does, it changes energy flow through the system for sure. It also changes hydrology, among many other things. Speaking of energy, cities consume a lot of global energy consumed by people. Some estimates put it up to 50%. Buildings themselves, by some estimates, consume 20% of our total human energy consumption. So these are very interesting ecosystems, and they're at the nexus of a lot of current day environmental problems. And so this is what green infrastructure attempts to deal with. So what's green infrastructure? It's basically environments or ecosystems created by people to provide tangible benefits that will combat some of the negative effects of urbanization. So this is the idea. I took this image from a textbook I use in my 4th year course called Environmental Remediation and Restoration. It's an environmental science course. And it shows one type of urban green infrastructure, which is some people call these bioswales. They're stormwater retention facilities. And essentially it's just, instead of letting the stormwater that runs off the street go right into the drain, there's this biological or ecological facility intercepting some of that water. So some of the water will be used by plants. It'll be transpired back into the atmosphere, so it doesn't go into the storm drains. Some of it will be infiltrated by the soil, so that will replenish the soil, and again, save on our costs of treating that water when it eventually makes its way through to our treatment facilities. Of course, it can cause erosion on the way as well, so there's lots of problems associated with urban hydrology, and this type of green infrastructure can affect that. But this stuff is costly, right? It costs money to put these in place, especially when we've already got, an expensive, city to maintain, that kind of thing. Adding these kinds of features makes it difficult to do it, okay? So it's because it's expensive. So one of the things we'll talk about today is, how can we improve the benefits without increasing the costs? We want to look at the life cycle costs of these technologies and compare them with, other technologies, because we want to find out if these are really providing a net benefit for urban developers. So you see this kind of green infrastructure springing up all over the place. It can be used as greenwashing. If you want to make your company look good, you can put a green roof on the top of it. Now this slide has several meanings, and I won't cover all of them, but it's actually nice that McDonald's thought, at least in Singapore, that they should put a green roof on top of their building. They may have been required to do this by law. There are certain areas that now have legislation, especially in really built up places like Singapore, requiring green roofs on certain types of buildings. And Toronto does that as well. But I'm asking questions about how this urban green infrastructure works. I'll focus in on green roofs because that's what I study here at St. Mary's, in addition to coastal barons and other stuff. So the services that green roofs provide to people, the reason we spend money building these things, thermal benefits, saving energy in buildings by cooling the roof in the summer and preventing some heat loss in the winter, reducing the amount of stormwater that leaves the building and has to be treated in our infrastructure, providing habitat, not just for plants, which is obvious, but pollinators, other important urban parts of biodiversity, I guess. They improve air quality, and they do increase the longevity of a roof, and we've seen some of these effects on campus as well. But like I said before, you've got to compare these with other technologies, and when you look at any one of these single benefits, pull one from the list, likely you can find another engineered solution that's probably more efficient or more cost-effective than a green roof. So for example, if you want to save energy on your building, well, double the insulation layer. It's a lot cheaper than putting a green roof on, okay? But, insulation doesn't do all these other benefits. And so this is, when you try to market green roofs, we say they're multifunctional. They don't just do one thing. They're entire ecosystems, and they provide a whole bunch of stuff. Nevertheless, we need to quantify what these benefits are. First of all, no one's going to spend the extra money unless they know, well, how long is it going to take this thing, before we can pay it off, right? What are our energy savings like, that kind of thing. Can we afford it, that kind of thing. An example of a case where sometimes the costs may outweigh the benefits are these fantastic examples of green infrastructure in France. These are green walls constructed by Patrick Blanc, who's one of these superstar architect designers of these things. They look amazing. They've got lots of species on them, but they're really expensive to maintain. These plants are dying and need to be replaced by hand constantly. They're not self-sustaining natural ecosystems where we can rely on seeds falling in to replace plants that die. They have huge inputs. They require a lot of water. And so when I say we want to look at the life cycle costs, this is what I'm talking about. You've got to figure out what your inputs are, how much does it cost to build, what are the energy costs, the carbon costs, the plastics required to build something like this, and does it actually give you some service that compensates for that over time? Not always. Drilling down into green roofs in particular and the thermal functions, basically it all comes down to heat flux, which is very simply the amount of heat moving from the outside to the inside of the building or vice versa. So in summer, heat is moving into the building. In winter, it's moving out. We want to make that net transfer of heat as small as possible because we have to pay money to cool our buildings if there's too much heat coming in the summer, and we have to pay money to heat the building if we're losing too much heat in the winter. And it comes down to this. It's a very simplified version of this equation. Heat flux is inversely proportional to essentially the insulative qualities of the medium that it's passing through. And it's also directly proportional to the temperature differential on the outside versus the inside of the building. So hotter outside, you get more heat driving inwards. Colder outside, you get more heat being lost. So this is data from St. Mary's Green Roof. We've been collecting, we have oodles of this data if anyone's interested in helping me analyze this. We've been doing this for years. But a lot of it looks like this. So this is summer. Each one of these peaks is midday. So this is basically a week in the summer. And on a conventional roof, we have these spikes. When it's sunny out, we're gaining a lot of heat. Positive values of heat flux on this graph mean that the building is gaining heat, and negative values means it's losing heat. And heat's going up out of the roof, essentially. The green roof, the fluctuations are much more dampened, so we're not seeing that extreme. Conventional roof surfaces, you actually lose more heat at night than a green roof because a green roof has more insulation, right? It prevents heat from leaving. But, very simply, if you're to integrate under these curves using the zero line as your axis, there's a lot more being gained than lost in the summer. So summer benefits in terms of cooling your roof are fantastic on green roofs. That's great. Of course, if you wanted the cheap solution, just put more insulation in your building and you won't gain as much heat. We looked at this in the winter as well because we have a lot more winter in Halifax than we do have summer. And I mean that in an economic sense as well. I think it's fair to say on a campus like this, the vast majority of our heating/cooling costs are going to come out in winter. Maybe Eric Spencer can back me up on that. I'm pretty sure that we pay a lot more in summer. Lots of our buildings aren't even air conditioned in the summer. So what we found, and this is again multiple years of data we've done this, it gets really complicated. It's not that simple to calculate the net benefits of some of this green technology. So when the sun is shining in the winter, a conventional roof actually saves you more energy. And it's better to have a black roof than a white roof because we're gaining heat from the sun when the sun is shining. When snow falls, our research has shown that the vegetation on a green roof traps more snow and you end up with a deeper snow layer than a conventional roof. And likewise, when the sun's shining, that deeper snow layer reflects useful solar radiation back into space, and so it's still better, even when there's snow, to have a conventional roof if the sun is shining. However, in a place like Halifax, the sun, as you may have noticed, is often not shining. So this includes nighttime, but it also includes a lot of our daytimes and a lot of, in winter, and I have data to back this up. I'm just not making this up. We have a weather station, we know when it's sunny and when it isn't. In this case, the green roof actually outperforms a conventional roof, which is great. So we're saving energy, and because the green roof, the vegetation component, traps more snow, a deeper layer of snow, even given the exact same amount of snowfall, we're saving more energy. There's an added bonus when there's snow, because there's going to be more snow on the green roof part. So that's great, but if you don't want to calculate the overall savings you're going to get from a green roof, you've got to incorporate all this stuff into it. You've got to know, how much snow you get in a typical year and all that kind of thing. It also means that depending on your climate, for this particular benefit, a green roof may not be the best solution. If you live in Calgary where you have a lot of sun in winter, a green roof may not be an optimal solution. But again, remember, that's just one benefit, right? We did the calculations, and for the St. Mary's, for something like the library roof, we're probably saving over an entire winter about $1 per square meter by energy savings in winter. It's not a lot, right? If you had green roofs on all your buildings in town, that might, add up to something significant. But what I argue with green roofs is that it's not until you add up all the other benefits together that you get something out of it. Yeah, Aldona.
$3 per square meter per whole winter?
Yeah. It's not a lot. I checked my figures a bunch of times. I thought I might have misplaced a zero or a decimal point. I think it's got to be more than $1 per square meter. It's more in the summer. I mean, if we were actually air conditioning the building, it's definitely more in the summer, because the differential between conventional roofs, especially when the sun is shining, is a lot more. And so Texas makes a lot more of a difference. Right?
So that dollar is just the energy cost?
Yeah. It's basically, it's calculated on, if you were to replace that heat that's lost. There's a lot of other complexity that goes into, how much your building's being used, that kind of thing, but it's just watts per watts, essentially. So, the other thing we realized, going through this is that, it's not just one technology versus another. Even within a green infrastructure technology like green roofs, what plants you use, the ecology of the system can make a big difference. So we've got, one species like this that traps a ton of snow, better insulation value, right, than this species. And we have data to back this up. It actually does make a real difference. So plant choice is key. As an ecologist, the other thing we've tried to do is look at, whether you have a monoculture on your green roof or a relatively simple ecology versus a more complex ecosystem there. And without increasing the weight of your green roof system, can we improve how a roof functions, what services we get off the roof, simply by planting different combinations of species? And we do find it. I'm going to have to go quickly through this, but essentially, this green one is monocultures, and these are all the mixtures of species. The ones with arrows were significantly better than the monocultures. And this is for a combined index of thermal benefits and stormwater benefits. Got to move on. But basically, plants provide a lot of the benefits of green infrastructure. And if you lose plants, if your green roof is too harsh, if you've really skimped on soil because your building can't hold enough weight, then plants are going to die and you're going to lose the functionality. You're going to actually get fewer returns on your investment. If you want to increase plant survival, one way of doing it, add more soil, or add inputs like irrigation, water, fertilizer, that kind of thing. but that diminishes the environmental overall life cycle benefits of a green roof, right? If you have to, spend carbon to have a viable green roof. So what we're trying to do is basically surf this trade-off between plant survival and adding too much to the green roof. We want to keep the weight low. We don't want to use municipal water supply to irrigate green roofs. Luckily in Halifax, you don't really have to do that because we get a lot of rain. So this is not a bad place for green roofs. So we use ecology to do this. I'm going to blow through this really quickly because we're running out of time. One of my master's students wanted to find out whether plants that were not very drought tolerant could have a better chance of survival if you plant companion species around them that may keep more water in the soil or otherwise benefit the species. And we have some evidence of this, so that's kind of nice, but it's an ecological solution. Everything else is the same weight of soil, the same amount of materials. A slight advantage, for this one plant species by companion planting. That's great. Some of my other students are looking at adding, relatively small features like logs. These are, cut out some invasive species that we cut out in my restoration course in the oaks, brought to the atrium green roof. It may trap small amounts of water underneath the log, creating a more beneficial microclimate that certain plant species may benefit from, that kind of thing. We've also got models of green roof performance that assume a green roof is uniform all throughout the roof. And so one of my honor students this year is looking at, he built a GIS model to calculate shade from adjacent buildings, and he's shown that this green roof, even though it's nice and open and we consider it generally a sunny site, there's huge differences in solar radiation over the year just based on shading from adjacent buildings. He validated this with a time-lapse camera. And so this is the model, this is predicted by GIS, and this is the actual shadow. These make a difference to the benefits you're going to get from the system. If you've got a lot of shade, those parts are going to perform differently. So what he did is took a whole bunch of plants and quantified the environment in each one of these target plants and showed, well, the shade creates this pocket of wet soil versus dry soil. It creates a huge difference in soil temperature. And this is what drives heat flux. So here we've got, this is the same day, mid-August, midday, 20 degrees soil, 21.4, up to 36 degrees soil, meters apart, just caused by shading. This has huge impacts on plant survival, so we need to know about this kind of variability, and huge impacts on the ecosystem services we get from this kind of green roof. So we need to study these kinds of things to better estimate the net benefits of this kind of technology. So to sum up, net benefits of green infrastructure are variable. They depend on a whole bunch of things like spatial variability, temporal variability, is it sunny, is it not sunny, all these kinds of things. Are there inputs? We can use ecology to improve the green infrastructure, especially when it comes to multifunctionality, to providing a variety of services, not just one, like with insulation, that just affects thermal benefits. We use these systems here for outreach and education, not just to encourage students to come to St. Mary's, but also as a showcase for the region. There's not a lot of green roof uptake here. It's expensive. We have a lot of old buildings that have roofs that need to be renovated even without a green roof, and so it's a difficult market. And finally, what I'm really interested in, we've been applying ecology, what other people have done in other systems, to green infrastructure. I'd like to find out if we can actually teach ecology something from studying these weird, constructed, artificial ecosystems. So I better stop. Thank you.